Okay, meet me again, and I'm here to answer some of the question in WhatsApp group about internal force and internal moment diagram, especially in the part where you have to decide where's the location of the cut and how many cuts that you need. Okay. Yeah. In order to answer this this question, okay, I need to remind you again that the basic principle behind cutting is whenever we have a structure and the structure is under load, then we want to find the distributed internal force and internal moment. Okay, something like this, for example, or this, or this. Okay, the things that we have to know is we have to represent the internal distributed shear force, internal distributed normal force, internal distributed moment, okay, with equation. Okay, so the end results that we want is something like this, something like that. Okay, in order to make it clear, I think I will just use blue pen. Okay, something like this or something like that. Okay, that is our end results. Okay, that's what we want. Okay, we want to find the distribution of the shear force along the length of the beam and the distribution of the moment along the beam as well. Okay, so this is the end results that we want. Okay, in order to get this particular results, we have to represent, okay, the distribution with equation. For example, in this case, okay, for this particular problem, okay, in this case, the shear force distribution from x equal to 0 until x equal to 0.3 meters is represented by this particular equation, which is constant equation. Okay, phi is equal to 0.625 kilonewton, this one. Okay, then for this particular part, the phi, the shear force, is represented by this equation. Okay, and the same for moment between 0 to 0.3 meters. The moment is represented by this particular equation, and at this location between 0.3 to 0.8 meters, the moment is represented by this equation. Okay, now why we have to cut twice? Okay, because remember that whenever we try to solve this kind of problems, okay, the equation there will not be able to be continuous all the time. What I mean continuous is from the left edge to the right edge. No, it will not. Okay, why? Because whenever there is a discontinuity, the continuous equation will stop, and we have to represent the next part with another equation. For example, it's like this. Okay, this one is one equation, and the other cut is another equation. This one is one equation, and the other part is another equation. So the first equation only works for x between 0 to 0.3 meters, and the second equation only works for x between 0.3 to 0.8 meters. Okay, and why the continuity of the equation stops? It's mainly because of discontinued load, discontinuity. Because of discontinuity. What I mean by discontinuity, there are several ways, there are several things that which cause discontinuity. The first one is concentrated external force. The second one is concentrated external moment. And the third one is discontinued distributed force. Okay. This is some of the example. You can see here that there is the input there will be P here and 2P here. Okay. The force there, force P and the force 2P there is concentrated force. That's why it will cause discontinuity. That's why, and beside that, if I draw the free body diagram, right? If I draw the free body diagram, this one for this particular problem, there will be AY, of course, there will be P here, and there will be 2P here, and there will be Py. Okay, after we solve it, we will know the direction of AY and By and the value of AY and By. But even though without knowing that, okay, without knowing the direction and the value, we will know that there will be a force there. There will be a force at the end, okay? So those two will cause discontinuity. Then this one will call the P there and 2P there will cause discontinuity as well. Okay, so in that case, if we want to represent the whole beam with equations which represents the internal distributed force and internal distributed moment, okay, I have to represent it with several equations because I will not be able to represent the whole things from left edge to right edge, okay, using only one equation. Why? We can't, because there are a lot of discontinuity. Okay, starting from AY, it's a discontinuity. Then after that, there is no discontinuity. So we can represent this one with one equation. But we have to stop at P because it gets discontinued there because there is a concentrated force there. So the first equation will walks from x equal to 0 until x equal to L4. Then after the discontinuity of due to the force P, we can represent with another equation. Okay, so this is the first equation. The second equation will walks from here to here, from x equal to L per 4 until x equal to, this one is x, right? So L per 4 plus L per 2 supposed to be 3/3. Okay, 3L per 4. Okay, I can represent this part, okay, with one equation. Why? Because there is nothing there here. There is no discontinuity there. But after it with the force 2P, there is another discontinuity because of concentrated force 2P. That's why I can't continue my equation. That's why after force 2P until Py, I have to represent with another equation. So the third equation is supposed to walk from 3L per 4 x until L. The whole length here is supposed to be L. Okay. Now we know that we can represent the whole distribution of internal moment and internal shear force using three equations. The first equation is for this. The second equation is for this, and third equation is for this. Okay, and if we combine it together, we will be able to find out the distributed internal force and distributed internal moment. And in order for us to know the equation for each region, region number 1, region number 2, region number 3, for example, okay, we have to cut anywhere in that region. So for example, I want to find the equation for region number 1. Okay, for region number 1. So for x equal to between 0 and alpha 4. So in that case, what I can do is I can cut anywhere from here to here, wherever you want, wherever you want. You can cut anywhere you want, as long as it's in between 0 and alpha 4. As long as the x is between 0 and alpha 4. Okay, but remember, when you cut, you have to represent the distance from the left side as x. Because why we have to represent the distance from the left side as x? Because I want to find, okay, the distribution, the equation in terms of x. That's why whenever I cut, for example, like this, right? The first cut, for example, this is my first cut. What I have there will be, there will be a y there. But I'm supposed to solve ay first before I'm doing this way. Then that's all. That's why, and phi positive is going like this, moment positive here like this. And you have to know, you have to remember to represent the distance with x from the left side. Remember, only from x is from the left edge, like this. Then after that, you will be able to find out the value of phi, the equation which represent phi. And then you can find out the equation which represent m in terms of x. By doing so, you will be able to find the equation which works for this one, from x equal to 0 to x equal to alpha 4. Then after that, you have to do another cut. Your other cut, the second cut, is supposed to represent the equation for the second region. In that case, you can do wherever you want as long as the cutting is between x equal to alpha 4 and x equal to 3 alpha 4. Like that. Okay, the same for the third one. You can do the third cutting anywhere you want as long as it's in between 3 alpha 4 and L. Okay, another example. This one, okay, we have concentrated force here. Then we have Py here, we have Ay here, we have distributed force. How many equations to represent the whole beams? Okay, from A to this particular distributed force, we can represent it with one equation. Then there is a discontinuity because suddenly a distributed force of 800 Newton meter appear. So we will not be able to continue the first equation. That's why we have to represent with another equation there. So this one is the second. Then you can do anyway. You can create an equation which represent from x equal to 2 meters until x equal to 5 meters. Okay, from here to here. Okay, then suddenly at the end of 5 meters, the distributed force stops. Okay, it's discontinuity distributed force. Okay, remember just now I wrote down 3 things, right, which can cause discontinuity. The third one as well, discontinued distributed force. Okay, the example of discontinued distributed force is at this part and at this part. That's why there is a discontinuity here. That's why we can't continue the equation, second equation. That's why we have to represent the next one with the equation number 3. Then after that, the equation number 3 can works for x equal to 5 meters until 7 meters. At x equal to 7 meters, we can't continue anymore. Why? Because suddenly there is a concentrated moment there which causes discontinuity. That's why we can't continue the equation. That's why the last one, from x equal to 7 meters until 9 meters, there will be the fourth equation. So total, we have 4 equations, which can be represented by 4 different cuts, something like that. And where you want to have the cuts, it's up to you. Equation number 4, you can do the cuts just slightly after 4.0 kilonewton meters or slightly before By. The same as equation number 3, you can get that by doing a cut just slightly after the 800 Newton per meter distributed force, or slightly before 4.2 kilonewton per meter, kilonewton meter, something like that. Okay, the normal way, we normally cut exactly in the middle of that region. Okay, not exactly in the middle, but roughly in the middle of that region. Roughly in the middle of that region. But remember, you can't represent the distance from left edge with certain value. For example, like even though here roughly is 2 meters plus 1.5 meters is supposed to be 3.5 meters, you can't put 3.5 meters there. We can't. Okay, for the second cut. Okay, for the second cut, something like this, right? So there is a distributed force, and there is a AY, and there is a shear force V and M, which we try to find out. Okay, the distance here, you can't put it as 3.5 meters. You can't, because you will not be able to get the equation. In this case, it means that you cut exactly at 3.5 meters. And we don't want that. What we want to know is if we cut it between 2 meters until 5 meters. In that case, what you're supposed to do, instead of cutting it exactly at 3.5 meters and putting it here 3.5 meters, you just represent the distance with x. The distance from the left edge with x. By doing so, later your results of V and M will be an equation of x, which will show us the shear force and internal moment distribution in terms of x. That's the equation that we need to do. Another example, this one, there will be two cuts because there will be discontinuity here. Then we can create the first equation. Then after that, there is a discontinuity here because of suddenly distributed force of 3 kilonewton per meter appear. So you will not be able to continue first equation. Then you have to do another equation, the second equation. The second equation is from x equal to 300 millimeter to x equal 800 meter, this region. This is the second region. The first region is here, from x equal to 0 to x equal to 300 millimeter. Okay, to represent the first region, just cut it anywhere you want between x equal to 0 to x equal to 300 millimeters. But remember to draw the free body diagram, and the distance is supposed to be x. Okay, this one's supposed to be AY, and then there will be V and moment. But remember, the distance is x there. Don't put a number there, because you will not be able to get it. You will not getting the equation that you want. Okay, then the second cut. Okay, if I try to do it from the left, this will be my free body diagram. AY, okay, distributed force of 4 kilonewton per meter. Okay, and the distance here is x. The distance from the left to the distributed force is 300 millimeter. And this distance, the distributed force only, is supposed to be x minus 300. Okay, then I have to draw the V and moment there. Then by using sigma Fy and sigma moment, you will be able to get V and M. Okay. Yeah. And this is the equation. This is the example. Okay. The first equation that you get. Okay. Remember, you can see here, right? This is the first equation for V. This is the first equation for M. This is second equation for V. This is the second equation for M. And you can see that, right? We will not be able to represent the whole beam with only one equation, because you can see, as I told you before, there is a discontinuity here, just where the distributed load started. The same, there is a discontinuity here in the moment, just where the distributed force started as well. That's the thing. Okay, so we have, like it or not, we have to represent it with two equations, like the way like I told you before. Okay, then for this problem, there will be three equations. Number one, number two, number three. For this one, there will be two. Number one, number two. This one will be three. This one will be another three as well. Okay. The point is simple. Just try to look for discontinuity. And in that case, you can represent the continuous part with one equation, then represent the other continuous part with another equation, represent the other equation, represent the other continuous part with another equation. From this to this, there is a continuous part. Here to here, continuous as well. It's continuous as well. Okay. All of those are separated by the discontinuity that I talked about. Okay, you can see here, right? There is one equation to represent from here to here, another equation to represent here to here, another equation to represent. Sorry, it's slow. Oh, yeah, here to here, right? The same for the others. This one, there are two equations, but just by chance, the shear force is continuous, but it's by chance. But remember, we can't do that for moment because there are two different equations there. Okay. Okay, the last problem that I want to talk about is this one. Okay, for this one, there will be three equations, right? Because there will be three equations. If you see this free body diagram, okay, from 100 lbf, there is a discontinuity here at 100 lbf. Then after that, they will be continuous until it reaches this particular point where the 50 lbf per feet started. Okay, so the first equation will walk from here to here, from x equal to 0 until x equal to 4 feet. Okay, this is the first equation. The second equation is supposed to be here. Sorry, the second equation is here. I didn't put it in the sequence. So third equation. Third equation walks from here to here, from x equal to 4 until x equal to 8, because the distributed force is continuous. But here is get discontinued because it suddenly appeared, and here it got discontinued because it suddenly disappeared. So it will, the third equation will only works for x equal to 4 feet this point until x equal to 8 feet this point. Then the last equation, second equation, okay, after the discontinuity, we have to represent the next one, the next part, with another equation. Okay, so it will work from x equal to 8 to until x equal to 12 feet, something like that. Okay, as you can see here, this is the results. Okay, from x equal to 0 to until x equal to 4, it's continuous and it's constant. Then there is a discontinuity here at where I told you before. Okay, because the graph changed from from constant to linear. Okay, then after that, at here, there is a discontinuity again. So the graph changed from linear to constant. The same for moment. At the beginning, the first equation is linear. The second equation is quadratic. The third equation is linear. So there is a discontinuity there, even though it doesn't look like there is a discontinuity, but actually there is a discontinuity there. Okay. So I think it's supposed to answer your question about where we have to cut it and how many cuts that we have to choose. Okay, I think that's all. Okay, thank you for listening.